All right, here we go with Descartes' rule of signs, the last of the three sections in 3.4 that we're going to be looking at. So we have looked at how to build a polynomial, and then so we have discovered that there are literally infinity numbers you can pick from to try when you're trying to find solutions of a polynomial. And then yesterday we looked at the rational root theorem, where we were trying to find, okay, what are all the possible rational numbers that could exist for my function? So we're trying to figure out how we can take that infinity set of numbers and continue to reduce them. So now we're going to use Descartes' rule of signs and hopefully continue to reduce those. So again, using that rational roots test, we want to find out all of the possible rational solutions. And then now we want to see, what can our solutions look like? What can our solutions sort of take the shape of? And when we do that, we want to say, okay, how many of each of these can we have? How many positive roots can we have? How many negative roots can we have? How many imaginary roots can we have? And that's what Descartes' rule of signs allows us to do. Okay? So, let's take a look at how this actually works. All right? Now, this next slide might look a little intimidating, but I promise you it'll make more sense as we go through it. All right? But here's something I want you to pause once I go to and write down. All right? Hang on one second. If we take a look at this, here is how this thing works. All right? Step one, we're going to write the function so the exponents are in decreasing order. Get it into that nice form that we like. Get it into that nice form that we like, decreasing order. And then, once we have it in decreasing order, we want to make sure that the last term in the function is a number. So the very last thing in our function, essentially we don't want it to have an x. If it does, we want to factor out all the x's from everything until that last term is just a number. So if our last term after we put everything in descending order is like x squared, we want to factor out an x squared from all of our terms. Then we want to count the number of sign changes in our original function. So how many times does our sign change? How many times does our sign change? Then we record that number as the maximum number of positive real roots. Okay, this will make more sense when we look at an example. Then we take negative x and plug that in to our function. And then we want to evaluate, see what new function we get. Once we get our new function, we want to count the number of sign changes in f of negative x. Then we're going to record that number as the maximum number of negative real roots. So we have a maximum number of positive real roots and a maximum number of negative real roots. Then we're going to add up the maximum positive and the maximum negative real zeros, and then subtract those from the total number of roots for the maximum number of imaginary roots. Or excuse me, minimum number of imaginary roots. Minimum number of imaginary roots. From there, we're then going to take a look at all the real roots that we have, and we're going to subtract 2 from it and get different possible outcomes. Okay? Again, we're trying to figure out ways that we can help to limit the number of options that our function is going to have. All right, so let's take a look here. If we take a look at this guy, actually, let me back up. What I would like for you to do now is pause. Pause and write all these things down. All right, I'm going to pause in 3, 2, 1, go for it. And we're back. Hopefully you wrote those down somewhere where you'll be able to look at them as we go through some of these problems. Okay, so step 1. So example 1. Step 1, we want to write that function so the exponents are in decreasing order. So we go 5 to 2 to 1 to 0. Good. 5, 2, 1, 0 is our exponents, and they're in decreasing order. Great. Wonderful. So now we want to say, all right, how many total exponents do we have? What's our biggest number of exponents, which will tell us how many total solutions we can have. In this case, our largest exponent, our degree, is 5. So we have 5 total solutions. And now we want to figure out how many positive solutions we have. All right, so if we go from 2x to 3x squared, this is positive, and this 2x to the 5th is positive. This negative 3x squared is negative, so that is a sign change. So there's 1. Then if we go from negative 3x squared to x, well, that's another sign change. It goes from negative to positive. And then as we go from positive x to positive 4, we don't get a sign change. There's nothing there. All right, so we count up the number of sign changes in f of x. We have two sign changes in f of x. One here, and one here. So we have two positive sign changes. Okay? So now we want to say, all right, let's find out what is in f of negative x. What's in f of negative x? So we say p of negative x equals 2 times negative x to the fifth minus 3 times negative x squared plus negative x plus 4. Once we have that, we then say, okay, if I take a negative number and multiply it by itself 5 times, we get that negative number, a negative times a negative times a negative times a negative times a negative. So 5 negatives make a negative. 2, so it's negative 2x to the fifth. And then, if we have this guy right here, well, negative x times negative x is going to be positive x squared. So this sign does not change. It stays at negative 3x squared. Plus a negative x, or just minus x, plus 4. So now we count our sign changes. Well, this is negative to negative, so there's nothing there. Negative to negative, so there's nothing there. And then negative to positive, so there's one sign change there. So we have one negative sign change. Okay? So we have negative, 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 positive. Oops. Let me undo that real quick. All right. And undo. Delete. There it is. Got it. Okay. So that was step 6. Step 7, we want to record that number. We wrote it down in our negative column. Good. Then we want to add up the maximum positive and the maximum negative real roots. So in order to do that, 2 plus 1 is 3, and then subtract that from the total number of roots to give us our number of imaginary solutions. So we have 2 positive roots, 1 negative root, and 2 imaginary roots. Okay? 2 positive roots, 2 imaginary, or 2 negative roots, or 1 negative root. 2 positive roots, 1 negative root, and 2 imaginary roots. So then our last step is we want to subtract 2 from the numbers of real roots and add them to the imaginaries to get our next set, to get all of our different solution outcomes. So this is one possible solution outcome where we have 2 positive, 1 negative, and 2 imaginary roots. But we could also take both of these positives away and end up with 0 positives, 1 negative, and 4 imaginary roots. See how these columns continue to add up to 5? They keep doing that. And now, since we have 0 positive and 1 imaginary, if we subtracted 2 from 1, we would have negative 1 solutions, which doesn't really have any kind of meaning. So we're stuck here. Whenever you get down to 0 or 1, you can stop subtracting 2. So these are possible solution outcomes of this polynomial. Okay, so that can help us to guide our picking when we pick from our list of rational from our list of rational solutions. All right, we could have 2, 1, and 2 positive, 1 negative, 2 imaginary, or 0 positive, 1 negative, and 4 imaginary. So with our rational root theorem, we have a bunch of positive and a bunch of negative solutions. If we're just plugging numbers in using synthetic division, and we find that one of our negative numbers is a solution, then we don't need to check any others. We don't need to check any other negative numbers, because this Descartes' rule of sign says that there's going to be, at most, only ever one negative solution, negative real number solution. So once you find it, you don't need to look for any more. Okay? So this is one way that we can use this to help us guide what we're picking. All right, so here, let's take a look at this function. 2x to the fifth minus 3x squared minus 3x plus 6. Is that literally the exact same? No, it's not. It's a different function. Good. That was close. Okay, so if we take a look at this, we say, all right, 2x to the fifth to negative. Okay, actually, let's go through steps. I gave you steps. Let's go through steps. So step 1, we want to write the function in decrease. So the degree is in. So the exponents are in decreasing order. 5, 2, 1, 0. It's in decreasing order. Wonderful. Good. Then we want to make sure that that last term is a number. So this last term right here is 6. Whoopsie daisies. I want to make sure that this last term right here is a 6, or is a number. It is. Good. Wonderful. Then we want to count the number of sign changes in x. Well, we go from positive to negative, so there's 1. Then we go from negative to negative, so that's still 1. And then negative to positive, so that is now 2. Two positive real solutions, possibly. And again, our largest exponent is 5, so we have 5 total solutions. Okay. So then we want to find how many negative roots we have. So we want to evaluate our function for f of negative x, or in this case, p of negative x. We're going to plug in negative x everywhere we see an x. 2 times x to the 5th. Whoopsie daisies. 2 times negative x to the 5th minus 3 times x negative x squared minus 3 times negative x plus 6. Okay, so if we have 5 or an odd number of negative numbers, it's going to change our sign. So negative 2x to the 5th minus 3 x times, or negative x times negative x is positive x, so it's not going to change our sign. So we minus 3x squared, and then 3 times negative, or negative 3 times negative x is positive 3x, and then plus 6. So we have we start out with a negative number, and it goes to a negative number, so we still don't have any sign changes. Then we go from a negative number to a positive number. So now we have one sign change, and then we go from a positive number to a positive number. So we have one sign change when we plug in p of negative x. So we have one negative root. Then if we take those two together, we want to add those up and subtract it from the total. So we could have two imaginary solutions. 5 minus 3 is 2. Now we want to subtract 2 from any real roots that have a number greater than or equal to 2. So we say, okay, well, if we have 2 positives, we could end up with 0 positives, one negative, and 4 imaginaries. So very similar to that last problem we looked at. Even though a sign change, and we also multiplied it by 3, it has the same sort of setup, the same sort of number of solutions. All right? So we're going to take a look at this example, and then I will give you an example to work on your own. I'm pretty sure. I'm like 60% sure that's how this is going to work. Okay? So again, we want to write the function so its exponents are in decreasing order. 4, 3, 2, 1, 0. Good. We have it in decreasing order. Then we want to make sure that the last term in the function is a number. It is. It's 4. Great. Wonderful. Then we want to count the number of sign changes in f of x. All right? So we take a look here. This is positive to negative, so that's 1. Negative to positive, so that's 2. Positive to negative, so that's 3. And then negative to positive, that's 4. Okay, so we have 4 positive sign changes. But if we take a look, we have 4 total solutions. So 4 positive sign changes. So hopefully you can sort of see what is expected to happen with the negative. But let's take a look and verify just to be safe. So we want to plug in p of negative x, 5 times negative x to the 4th minus 3 times negative x cubed plus 7 times negative x squared minus 12 times negative x plus 4. All right? And now we have negative x to the 4th, which is going to be negative x times negative x times negative x times negative x. 4 negatives make a positive, so we have 5x to the 4th. 3 negatives make a negative, so negative negative 3 is positive 3. 2 negative x's make a, negative 3x cubed. 2 x's make a positive, so positive 7 times positive x squared is positive x squared, or positive 7x squared, positive 7x squared. And then if we have negative x times negative 12, that's going to be positive 12x. Then 4 doesn't change because we haven't plugged anything into it, so 4. So now we count our sign changes when we plug in p of negative x. P of negative x equals this. So we have positive to positive. So we have positive to positive, positive to positive, positive to positive, positive to positive. We have no sign change. We have no sign changes. So this means that we have 0 negative solutions. So when you have that list of rational numbers that you can choose from, you know immediately, you can just, by doing this Descartes rule of signs, you can throw out half of those. You can throw out all the negative numbers. It can't be any of those, all right? So we then take our number of positive solutions subtracted from our total. So 4 minus 4 is going to say, all right, well, if we have 4 positive solutions, we have 0 imaginary solutions. But we also need to subtract 2. We also need to continue to subtract 2 whenever we are able to. So if we have 4, we subtract 2. We could have 2 positives, 0 negatives, and 2 imaginaries. We still have a number bigger than 1 here up in our positives, so we could also have 0 positives, 0 negatives, and 4 imaginary solutions. Okay? So this is saying 1, 2, or 3. These are all of the possibilities for what our solutions are going to look like. We'll either have 4 solutions that are all positive real numbers, or we could have 2 solutions that are positive real numbers and 2 imaginary solutions, or we could have no positive real solutions, no negative real solutions, and all imaginary solutions. Okay? These are all independent possibilities for the zeros. These are all their own thing, okay? So keep that in mind when you're using these, when you're trying to figure out what goes where, all right? These aren't all of the actual things that are what's happening. These are all the possibilities of what could happen, all right? So you have 3 possible outcomes, okay? So go to example 4. Thank you so much, Smartboard. You're my friend. Okay, so now I want you to give this one a shot on your own. Okay, give this one a shot on your own. Just follow those steps that I gave you, and then I will be back with the solution. I'll be back to talk through the solution. Okay, what are all of the possible outcomes for this? Okay, be right back. Okay, we're back. Here's what your solution set should have looked like. You should have had 1 positive, 2 negative, and 3 imaginary, or 1 positive, 0 negative, and 5 imaginary of our total 6 solutions. Okay? Poop. I missed step 1. Okay, let me fix this. Be right back. Okay, so step 1, write out the exponents that they're in decreasing order. Did it, check mark. X to the 6th, x squared, and 5x. Those are in descending order. However, totally skipped over step 2. That's 100% my bad. So what we want to do is factor out the thing that's going to make this negative 5x just a number. So we factor out an x. All right. For the most part, we're going to ignore this. This is a 0 solution. X equals 0 is a solution of this particular graph. Whoops. Where'd you come from, little 7? Go away, please. Thank you. Bye. Okay, so this is the new function we're going to look at. 6x to the 5th minus 2x minus 5. So if we look here, there are 5 solutions. So that's our total number of solutions that we're going to be looking at that can be either positive, negative, or imaginary. All right. So in this little parentheses right here, we start off 6x to the 5th minus 2x, so that's positive to negative. There's 1 sign change. Negative to negative, we stay at 1 sign change. So there's 1 positive real root. And then when we plug in p of negative x, we're just going to look at the part in parentheses. Okay, when we plug in p of negative x, we're just going to look at the part in parentheses. So this is negative, so 6x to the 5th, so x, or negative x times itself 5 times is going to give us a negative number. So negative 6x to the 5th, the sign's going to change here. And then we have negative 2 times negative x, which is going to be positive 2x. So the sign's going to change here. And then the sign is not going to change for our constant term. We take a look here, we have a negative to a positive, which is 1 sign change, and then a positive to a negative, which is 2 sign changes. So we could have 2 negative real solutions. And then that leaves us with 2 imaginary solutions, 2 imaginary number solutions. Or we have 1 positive real solution, so we can't subtract 2 from that because negative real solutions doesn't really make any sense. But we have 2 negative real solutions, which we can subtract 2 from to say, well, we could potentially have 0 negative solutions. which then gives us 4 imaginary if we have this scenario. Okay, 1 positive, 0 negative, 4 imaginary, or 1 positive, 2 negative, 2 imaginary. These are the two possible types of solutions that we can have. Okay, so I apologize for messing that one up. Let's give this next one a shot and see if this one goes any better. All right, cool. So x to the fourth plus 13x cubed minus x plus 5. Go ahead and pause it, and I will be back to talk through the solutions. Ready, set, go. Okay, so we're back. This is what this should have looked like. Okay, so we say we have 4 total solutions because we have a degree of 4. And then when we take a look at our positive real solutions, when we take a look at our possible positives, we have 0, 1, 0, 1, 2 sign changes. So we have potentially 2 positive real solutions. Then when we plug in negative x, we get x to the fourth minus 13x cubed plus x plus 5. So we have positive to negative, that's 1 sign change. Negative to positive, that's 2 sign changes. And positive to positive, that is not a sign change. So we have 2 potential negatives. So 2 plus 2 gives us 4. 4 minus 4 gives us 0 imaginary. If we have 2 positives and 2 negatives, we end up with 0 imaginary solutions. So now we need to look and see what are all the possible outcomes that we could be dealing with here. If we have 2 positives, we could potentially have 2 negatives. We have to take 2 away from this. We could potentially have 2 negatives and end up with 2 imaginaries. Or we could take 2 away from the positives, end up with 0, and have 2 negative solutions, and have 2 imaginary solutions. Any of these are possible. Also, this last condition is possible, where we could have 0 positive, 0 negative, and 4 imaginary solutions. So I get how this might feel like it's not all that useful. But again, once you find a positive solution, you know you have at least 2. Or if you find a negative solution, you know you have at least 2. So it can help you to stop guessing at some point. And also, it might tell you there might not be any nice numbers that you can plug in, and you might need to work with some imaginary numbers. Okay? So we want to come up with all those possible sets of solutions. And remember, each of these columns is its own set of solutions. You can't have both of these at the same time. Like there's never a situation where you could have, there's never going to be a single function where it has 2 positives, 2 negatives, and 0 imaginaries, as well as 0 positives, 0 negatives, and 4 imaginaries. Each of these is exclusively going to happen. One or the other is going to happen. Okay? They are not all able to be intertwined. Okay? Let's take a look at this one. I think this will be the last one we practice before we start trying to pull it all together. Okay? Give it a shot, and I will be back to talk you through the solution. Okay, so if we look at p of x, we notice that x to the fifth is our largest exponent, which gives us 5 total solutions. And then if we count the sign changes, we say, all right, positive to positive, that's 0. Positive to negative, that's 1. Negative to positive, that's 2. Positive to negative, that's 3. 3 total sign changes. So we have potentially 3 positive sign changes. Then we plug in p of negative x. I've taken a shortcut here that we're going to investigate and figure out how you can take as well. So when we plug in p of negative x, we get this as our new function. Now we want to count the sign changes for this, for our potential negative solutions. We have negative to positive, that's 1 sign change. Positive to negative, that's 2 sign changes. Negative to negative, we're still at 2. Negative to negative, still at 2. So we had 2 negative sign changes. 3 plus 2 is 5. 5 minus 5 leaves us with 0 imaginary solutions. But remember, we want to always subtract 2 whenever we have numbers that are bigger than 1. So first, let's pretend like our positive numbers didn't change at all. Our positive solutions didn't change, but we ended up losing our 2 negative solutions. So then we had 3 positives, no negatives, and 2 imaginaries. Then we said, okay, well, what if, since we can't take away any more negatives, let's see what happens if the positive signs change. If we take away 2 from our positive solutions, we're left with 1 positive solution, 2 negative solutions, and 2 imaginary solutions. So that could be what would happen if we lost two of our positive solutions. Now we have to investigate what would happen if, and then because we can't keep subtracting from 1, and we can't keep subtracting 2 from 1 and get anything that makes sense as far as solutions go, we stick with our 1, subtract 2 from our negative solutions, and we're left with 4 imaginary. So 1 positive, 0 negative solutions, and 4 imaginary solutions. So we want to try to find all the different solution spaces that exist for this function. Okay? So let's start pulling things together. Okay, let's start pulling things together. So let's take a look back and see what happened to our different signs. All right, hang on one second. There we go. Sorry, things got a little weird. All right, so if we're making our connections, let's see. Well, first off, from here to here, make a mental note of what the exponents of the signs that changed were. What was the exponent? What was the number of the exponent of the signs that changed from p of x to p of negative x? Got it? Okay. Jot them down on a piece of paper. Yeah, mental notes are not all that useful. Yeah, jot them down on a piece of paper. Okay. What was the exponents of the signs that changed? What about this one? What exponents changed? Write it down on the same piece of paper. This one? How about this one? What about this one? And finally, this one. So, after you've jotted down all those numbers, what types of numbers change when you are plugging in x of p of negative x? Well, it just so happens that whenever you say f of negative x causes all of the odd numbered exponents to change sign. Even exponents stay the same. Okay? So whenever you plug in f of negative x, all those odd numbered exponents are going to change sign. The even numbered exponents are going to stay the same. Okay? So that's the first thing. Second, what were all of the imaginary number solutions? What were all the imaginary number solutions? Jot them down. Jot them down. Jot them down. Same thing. One more time. And of course, by one more time, I meant one more time. So what were all of the even numbered solutions? Or excuse me, what were all of the imaginary number solutions? What types of numbers were those? Okay. So, imaginary numbers always show up in even amounts. So that's something that can help you and see if you're on the right track. All right? F of negative x is going to force all odd numbered exponents to change. Then, all of your imaginary number solutions should always show up in even amounts. And that's something we talked about when we were building polynomials, about how we always have an even number, a positive and negative version of all of our imaginary number solutions. So it hopefully makes sense that those imaginary number solutions are always going to show up in pairs or in even numbers. Okay, let's take a look at one more, and then you can just go ham on your homework. Okay, so let's take a look at this one. Try it on your own, and I'll be right back. And we're back. Go away, number 7. Why do you keep showing up? Go away. All right, so if we take a look at this, we see that there are 5 total solutions because 5 is our largest exponent. And then if we count our positives, our sign changes for p of x, well, we see negative, 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 negative. We don't change sign ever. Not ever in life. So we have 0 positive real solutions, which means that all those positive numbers that you find for the rational root theorem, you could throw all those out. You don't need any of them. And then when we plug in negative x, we see positive number, positive number, positive number, and then a negative. So we have 1 sign change for our negative side, which means that we have 0 positives, 1 negative, and 4 imaginary solutions. Now, we can't take 2 away from 0, and we can't take 2 away from 1, so there are no additional solution spaces. There are no additional types of sets of solutions that we can have. So this is it. 0 positives, 1 negative, and 4 imaginary. So once you find that 1 negative solution, you can just start looking for imaginary solutions. All right. Hope this was helpful. You can go ahead and get started on your on the assignment, which is attached to this particular Canvas or this particular Google Classroom recording. Have a good one, and I'll see you in a few days. Bye, guys.